this conference online a year ago, and it's even better. Great to be here in person. Hope to taste some wines as well. And it's great to see many people I know and miss talking to in person. I want to talk about measurement-induced phase transitions, but from a very different kind of measurement-induced phase transition than was discussed, than Matthew talked about. Measurement-induced transitions basically without dynamics, just in ground states. And this is work done with Sam Garrett, Zach Weinstein, and Rohit Sajid. At the end, I want to give you some teaser on a different problem that turns out to can use the same tools as this and has to do more with topological states in topological mixed states. Hopefully, I'll get to the teaser. Why is this doesn't work? Oops, now it does. OK, so I won't give a big introduction because Matthew gave a great introduction. There are really great new platforms now that can show us hidden aspects of many-body systems, like entanglement, showing entanglement entropy, string correlations, quantum measurement, and scrambling. Somehow this doesn't work so well. And I want to now focus on the possibility of maybe making continuous or non-demolition measurements on quantum systems that you prepare. For example, quantum systems you prepare with cold atoms in their ground state or close to their ground state, and then make measurements on them. So why are measurements interesting? First of all, it's a fundamental part of quantum mechanics, and it has a very strange, as you know, dynamics in quantum mechanics. It collapses the wave function onto one of the eigenstates of the measurement operator. And this quantum collapse can destroy quantum correlations, as it does in this cat state, or as it does when you measure one component of the Bell pair. It destroys the correlation and gives you a classical state. On the other hand, measurements can also create quantum correlations that weren't present initially. For example, in quantum teleportation, we have shared Bell pair between one lab and another lab, and this other lab also shares another Bell pair with a third lab. If in this lab I make a local measurement in the Bell basis, then after the measurement, I created correlations between these two distant labs that were previously uncorrelated. And the question is, how does this play out in this kind of tension between destroying correlations and creating new ones plays out when you try to measure many body states. So for example, if you have a many body wave function created as a ground state of some system, now you measure it partially, what happens to the correlations in that state? So let me try to, well, I'm not going to talk about previous work, but this is just, there was previous work by the community about measurements and how they affect quantum states. One of them you heard a lot about now, measurement-induced transitions in hybrid quantum circuits. A related problem that maybe is slightly a bit more connected to what I talk about now, but not exactly, is this work on measurement-induced finite time teleportation transition. But today I want to talk about something a bit different and maybe even simpler. So how do partial measurements affect a quantum ground state? How do they change the long-range correlations on that state? And I'm going to focus on, for the first part of the talk, on critical ground state. So I have a critical ground state, kind of represented maybe as a tensor here, and I do partial measurements on this state. And I want to ask, how does it affect the long-range correlations in this critical state? First example I'm going to discuss is a critical 1D quantum gas subject to some non-demolition measurements using light. And the second example is a critical 1D transverse field Ising model. And you see that actually there is non-trivial effect of the measurements on this critical state. The second part, which I probably will have time for only a teaser, and is rather different, but it turns out that the same technology helps understand it in a very simple way. Phase transitions induced not by measurements, but by local quantum channel applied to a quantum ground state. And in particular, I want to show you that this can describe a topological transition between transitions between different topological mixed states. And this is work with my student Imu, Ruha Fan from Ashwin's student, and Ashwin in Harvard. Okay, so I'll start with the first part. Oops. So the first example is going to be on measurement of 1D quantum gases. They were realized some time ago in ultra-cold atoms. This is an example in Emmanuel Bloch group from quite many years ago now. Just as a reminder, one-dimensional quantum liquids, either fermions or bosons, are all described at low energies and long wavelength by a universal long wavelength field theory, a critical field theory called Luttineger liquid. It can be described in terms of the fluctuations of the phase. So for example, if these are bosons, if they were superfluid, the phase would be uniform. But since it's a 1D system, the phase is fluctuating, and you can describe the low energy physics by harmonic fluctuations of the phase. And this parameter K is called the Luttinger parameter, and it determines the long distance decay of power law correlations in the system. Okay? A dual description is in terms of the density fluctuations, or more precisely, this field phi is the field that describes the displacement of atoms from putative equilibrium positions, and it's closely related to the density fluctuation. So the density fluctuation is, the smooth part of the density fluctuation is gradient of phi, and then there are oscillating parts due to the fact that, the atoms are discrete. So there is an oscillating part of the density fluctuation. So this is a long wavelength description of the density, and it has, again, harmonic theory, but now the same Luttinger parameter appears in the denominator, so it's a dual theory. If you're classical in terms of the phase, you're more fluctuating in quantum in terms of the atom positions and vice versa. So it's a dual description. So this is just as a review, to remind you. And yeah, the Luttinger parameter in this case, k equals 1, corresponds, for example, to non-interacting fermions or hardcore bosons. K less than 1 corresponds to repulsive fermions or bosons with sufficiently long-range interactions, and so on. Okay, so we want to understand how measurements affect the correlations. Before we're doing the measurements, in the ground state, we know that the correlations are a power law, so the smooth part of the density, for example, has this correlation function, 1 over x to the power 1 over x squared, completely universal, and then non-universal but power law correlations in the oscillating part that go as 1 over x to the power 2k, and can continuously tune the exponent by, for example, tuning the interaction strength that in turn tunes the Luttinger parameter k. So you have a continuously tunable critical theory in this case. And our question, and phase correlations similarly have a power law decay, also set by k, and not too surprisingly as 1 over k. All this is, of course, very, very well known. It was even seen, the power law decay of correlations is even being demonstrated in this pretty old experiment already by Emmanuel. So, okay, now we're going to introduce measurements, and the kind of measurements I want to look at are sort of realistic in this kind of situation. I want to do weak measurements of the density everywhere in the sample, So we have some probe light that interacts weakly with the particles, and you can think of it in this way. So if the light goes out with 0, basically unchanged polarization, for example, then it means that either the light didn't have a chance to interact, or there was no atom in that particular position. On the other hand, if there was an atom in that position, it could still go out as 0 because the interaction is weak, so the change in polarization is a small angle. And if you measure the orthogonal polarization, sometimes you'll find 0. But if you find 1, it actually for sure means that there was a particle occupied there. Okay? This is called Homodyn detection. And this is the kind of detection I'll assume for most of, of this part. And then the question is, how does this partial measurement affect these correlations? Note, importantly, there is no dynamics at all. We're given a ground state. One second. We're given a ground state, and now we're measuring it fast and evaluating the correlations right after the measurement. Yes, Eugene? Good. Yes, so smaller. So in the end, to simplify things, I'm going to look at a particular measurement pattern where I have a 2kF oscillating pattern of where I measure oscillating at 2kF. That will be the simplest case, but in general, I want to measure at higher resolution than the interparticle spacing. Yeah. Hard maybe, but it's just where, yeah.
That's a naive question. Normally, I think of Homodyn as projection onto the X basis space oscillator, but it looks like.
Yeah, so one can think about this as if you want to think about it realistically, it's like a Faraday rotation of the light, and I'm measuring now the polarization of the light in a perpendicular polarization to what it was before. So it projects me, and the coupling of the light is to the density of the particles, I think. So how to exactly map it to a kind of completely realistic coupling, I'm not exactly sure, but I think that is sort of realistic enough for what I'm going to say.
Yeah, it's very realistic. Just wondering about the word.
Yeah, okay. So, yeah, so it's like partial measurement of the density, weak measurement of the density. And now I'm going to, for part 1 of my talk, I'm going to specialize to a simple outcome. So again, the measurement outcomes are specified by strings of 0s and 1s, but there is one special string of 0s and 1 where you have all 0s. This is like the no-click situation. It's actually, if the interaction is weak, it's not so rare. Well, it's still exponentially rare, but compared to other outcomes, it's less rare. And it doesn't mean that you don't have a particle anywhere. It's just that the interaction is weak, so likely you haven't seen the change in polarization. So this no-click state, what it does, it can be described as imaginary time evolution with the density, or delta n, actually. It's the change of density operator. And it basically weakly biases you towards having no density at some point, right? And if, and that comes to Eugene's question, I take this measurement strength and oscillate it in space with exactly the right spatial frequency, then I can write this in the long wavelength limit as a cosine term. Okay, so this is for simplicity what I'm going to look at first, but we can make it much more general than this. I'll try to generalize in a minute. So let's look at this no-click situation. What does it do? Well, I want to calculate the correlations in the no-click wave function, right? So how do I write the no-click wave function? Well, I can write the no-click wave function by taking some reference state. It really doesn't matter what it is. It could be a trivial state, some product state. I apply an infinite time evolution, imaginary time evolution with the Luttineger liquid Hamiltonian. Then I have to apply the no-click projection. I should have flipped them around. Then I apply the no-click projection. And finally, I measure the correlation function, and I sandwich with the same state on the other side, and I can rewrite this whole thing as a path integral. And then it's when I write this whole thing as a path integral, it's basically averaging over delta n with some effective action that I call the no-click action. It's the path integral representation of this imaginary time evolution. Yes. Yeah, you need to, well, there is only one Hamiltonian I need to trotterize, which is really this. Yeah, I wrote it in a kind of sloppy way here. I really have to first apply the imaginary time evolution with this, then after that apply the other one, trotterize, and do the, write the transfer matrix, take the continuum limit and write it as a path integral. And it's not written very it's written too concisely and sloppily here, but in the end, the result, when you do it properly, is basically this. And the no-click action that you get is, I'm going to show it if it flips. Okay, this is not working. Okay, so the no-click action I get is basically just the Luttineger liquid action plus this correction. Note that here there is no integral over imaginary time, only an integral over space, no imaginary time. So this is actually quite reminiscent of another well-known action of a quantum impurity problem. If you have a quantum impurity in one point in the Luttineger liquid, then there is a famous problem that Matthew Fisher and Charlie Kane looked at in the 90s. It has the fate of a Luttineger liquid with a single impurity in the ground state. Here, instead of being in all space, this cosine term is in all time, all imaginary time at one point in space. So really, you can view it as a rotated Kane-Fisher problem. This is the impurity problem. The impurity is a defect in time at one spatial point. And this is a defect in all space at one temporal point. Okay, so, and since there is weak rotation, it's basically the same problem. And one can analyze it in the same way and then do the interpretation properly. Yeah.
Is the reason why you are interested in the same time correlation as opposed to different points in space and time correlation?
Because I have a ground state. Someone gave me a ground state, no dynamics. And now I'm interested in the spatial correlations in that ground state. There is no dynamics. There is no point in looking at temporal correlations, right? I just have a ground state, no dynamics. So I'm looking at, I'm asking the question, how do measurements affect my ground state correlations after measurement? And you can do the scaling analysis just like in Kane-Fisher, and you'll not be surprised to learn that when the Luttinger parameter is greater than 1, then the measurements are irrelevant. And what this means is that if I now evaluate in the measured state, no matter how strongly I measure, if I look at sufficiently long-range correlations, they'll not be affected by measurements, and they'll be exactly the same as before. In some sense, this is not surprising because I've measured just 1 second for a finite time. Then you'd say, well, if I measure for a finite time, how am I going to affect things that are way beyond my light cone? So not surprising that I'm not going to affect my correlations. Just one minute, I just finished this transparency, and then, but now you go to k less than 1. Oops. K less than 1, you find, no, the measurements are relevant now. And in fact, you do have a non-perturbative effect on the long-range correlations. And you can evaluate these correlations now by going to the strong coupling limit. I'm not giving the details, but one can evaluate them and see that you change the correlations non-perturbatively to this. So they now decay faster than they do, but there is still a power than they did before, but still a power law. Yes?
Just a clarification, this rotation in space-time, the impurity now is at the boundary.
The impurity is now a boundary. Yeah, absolutely. It's an impurity. It's not, instead of the impurity being in space at one point in space and everywhere in time, it's everywhere in space and one point in time.
At the initial time.
Yeah, but there is no, it's all imaginary time, right? It's all equal time correlation functions, and the imaginary time came from producing my ground state, right? So it's all imaginary. There is no real-time dynamics whatsoever here, except for the measurement dynamics, if you want, right? Yeah. I'm doing, right, so I'm applying my light for a very short time, and then evaluating the correlations.
But this is essentially like some projection operator.
Yeah, it's a projection operator on the light, right, which is a partial projection operator on the system. The light is projected to the state 0, and then the wave function of the light, and that gives you a partial projection because of the weakness of the interaction with the light of the system wave function to something that we're now looking at, right? So, yeah.
Specify the time it takes to do the measurement, result, and the time measured.
There is no time here at all. Yeah, I measure fast. I mean, I measure at scales that the light, I measure fast, and because the interaction with the light is weak, then the measurement gives me a weak, it's usually going to be a weak measurement.
It is the measurement. Okay, when you understand it, so you think about it as measuring the correlations immediately after,
Yeah.
After you
Right. Yeah, you can think of the light as little ancillas that I turn on a unitary coupling between them for a short time. Unitary coupling between them and the density. So they rotate, the ancillas rotate by some angle. And then I measure at a perpendicular angle to where they were in the Bloch sphere. And that's basically my weak measurement.
No dynamics happening.
No dynamics whatsoever, right? So no Hamiltonian dynamics. The only Hamiltonian dynamics is the generation of the ground state. Okay, so that's why there is only imaginary time evolution here. Okay. Here I simplified and looked only at this phase transition onto a phase transition where I projected onto one measurement, possible measurement outcome. I can make it more general, and in this case, actually, I don't even have to do this artificial thing where I pattern my measurement to be commensurate with the interparticle distance. I can measure and just average over the entire measurement ensemble, and then just like in Matthew's talk, when you have to measure over average over measurement outcomes, you have a problem of denominators. You need to use replicas, and then the problem starts to get a little bit more tricky. So again, you have imaginary time evolution to prepare your state, but you have n replicas of your state, and at the point where the measurement occurs, the measurement couple all these replicas. So this spatial at zero time impurity, what it does, it only at that point it couples between the replicas, and you can now do again a scaling analysis to check when this coupling between replicas becomes relevant, and you see that actually this becomes relevant at k. Oh, where is it? Somewhere. Oh, yeah. This becomes relevant at k equals half. And you see that the correlations are changed only at k equals half. So k equals 1 now, the measurements are always irrelevant. Well, I want to go through the next example rather quickly because I want to get to my teaser at the end, which is a different problem, but the same technology actually helps. So just quickly, first of all, the example 2 is one-dimensional critical transverse field Ising model. And again, I do homodyn detection where you can imagine that in principle, in this homodyn detection, I can either detect a domain wall, which is basically the measurement operator is zi plus 1, or detect an odd parity, a spin flip in the x direction from x to minus x. So these are the two possible symmetry conserving measurements I can do, and I can ask what does it do to the Ising correlation function, which in the critical Ising state decay as 1 over x to the 1/4. And again, you do the same, exactly the same, you go through the same analysis, and you see that measuring this correlation function in the no-click case is basically like taking a two-dimensional statistical mechanics model, Ising model, classical Ising model, and at the point tau equals 0 and x everywhere, you place a defect, and the defect is either stronger bonds or weaker bonds at this point. And you can ask, what does this do to the correlations? Well, this is well known. A one-dimensional defect in a two-dimensional Ising model is exactly marginal. You can see it from scaling. You can see it from exact results by McCoy and others in the 70s. And it's exactly marginal perturbation, which means that the prediction is that it will continuously vary the measurement strength. The measurement strength will continuously vary the power law correlations. And indeed, we can do it numerically because the transverse field Ising model is mappable to free fermions. We can calculate this numerically, and this is exactly what you see. As a function of the measurement strength mu, you get you continuously change the power law, which is exactly what you expect. There is something that goes beyond the classical model, which is we can calculate the entanglement entropy using this free fermion theory after the measurement outcome. And what you see is that the entanglement entropy has a log scaling, but a log scaling that also changes continuously with the measurement strength, starting from what you have for the CFT, right? C over 3, where C in this case is half, so this slope is 1/6. Yeah.
Can you compare with the value, the CFT scaling with the defect?
CFT scaling with defect, is there a value for, I wanted to ask you about this because I know nothing about this. Okay, let's talk about this, right? So, yeah, anyhow, so, anyway, we can do the same thing for an ensemble of measurement outcomes. Then it's again, a cake will, we find that then the measurements are always irrelevant. And again, we see it in numerics. We see that at short distances, the correlations are changed by the measurement, but at long distances, they're not changed at all. Now I want to give you the teaser. So I'm going to skip the summary and open questions and just give you this open question. Are there phase transitions in this case that are tuned not by measurements, but by actual decoherence? And the answer in this case, unlike maybe in the measurement-induced transition so far, is that yes, there is, and it's actually very interesting. So now we're going to do something very similar. So, and it doesn't have to be topological states, but somehow it's especially interesting in this case. I'll show you why. But now we have a fairly similar starting point. We start with the ground state. We have a ground state at our disposal, but this time the ground state is topological. For example, it could be the toric code ground state, or it could be the ground state of an Ising CFT, so two-dimensional non-abelian topological state. Okay, it could be either that or that. Just as an example, keep in mind for a second the toric code. Okay, so we have a toric code, and I write it as a pure density matrix for a reason, because now we're going to apply local channels to it, a local channel. For example, X channel. And we ask the following question. After applying the channel, is there still topological order in the mixed state in some sense? Is there a critical gamma at which the topological order is lost? And how to diagnose mixed state topological order even? This has, for those, some of you may recognize that might have something to do with, well, it has something to do with error thresholds in these topological codes. But here we're trying to ask more general questions and in any kind of topological state. And the channel, so the answer, first of all, a simple answer can be the channel can always be represented as a finite depth unitary if we purify it with ancillas. And this finite depth unitary cannot change the topology. So you might say, well, observables, that there is no change in the topological order. If it was topologically ordered before, it's topologically ordered after applying the channel, no matter how strong, as long as it's a finite depth unitary. So that actually only means that observables that are linear in the density matrix are expected to show topological order for all gamma in this channel. The channel could be anything. This is just an example of a channel where I have local X errors. However, we're going to see that there is a topological transition induced by the quantum channel nevertheless. Let's see why. So now we have a density matrix, and it's nice to represent it as a vector, as a state vector, by taking the ket and bra and putting them in the same direction. So the pure state is just a doubled system, psi. And the ground state is prepared by imaginary time evolution with this decoupled Hamiltonian, H cross I cross H. Again, I prepare the ground state with imaginary time evolution. You see very similar to the case of measurements on ground state. Now, apply the channel. The channel is applying these Krauss operators on the two sides, on the two sides. So each side here is, has two toric codes because I have one for the ket and one for the bra. Even the top side is two independent toric codes. But at this position where the impurity is the quantum channel, only there I couple these two toric codes to one another. And in the end, I'm going to have another part at the bottom because I'm going to calculate some correlation. So stay tuned for that. But for now, you see only one side. But even this one side is a doubled system. And the doubled system is connected only at this boundary impurity. And I can rewrite this boundary impurity, if this is the toric code, as creating a pair of electric excitations, electric anions, both on system 1, both on the ket and on the bra side. And then putting one on, basically hopping an electric charge from one point to the other. So what does it do? This can lead, because it basically creates hopping of anions on this defect. If it's strong enough, one can imagine that it will give rise to condensation of anions. But since it's only hopping pairs of anions on the two systems, 1 and 2, ket and bra, it will always create pair condensation of anions. So you have, actually you find a phase transition. Right, you find the phase transition where you have anion condensation on this defect, two-dimensional defect in the three-dimensional participatory code. And it's diagnosed by an order parameter, which is basically the string order parameter, electric, or if it was ZZ, it could be magnetic correlation. It's a string order parameter, and you need to normalize it by a closed string. It's the same order parameter that was used by Misha Lukin's experiment recently. However, here, because we're dealing with the mixed state, we have to double it. And remember, this we're diagnosing pair condensate of system 1 and system 2. So we need to double the open string, OO, and we have to double the closed string, CC, and we apply this correlation function from the two sides of a density matrix on the two sides. So if you write it in a more familiar notation of just density matrices, it's trace of rho, EI, R plus 1, so I plus R. So electric, you create on one density matrix a pair of distant electric excitations on the two sides of the density matrix. It's a quantum channel. And you overlap it with another density matrix where you haven't done that. This row is the density matrix. Both of these rows, of course, are the density matrices following the quantum channel. And what you find is a phase transition in this correlation function. Yes. Everywhere. No, the fact that it's only here at tau equals 0 is exactly like in the measurement problem, right? Because you have a three-dimensional partition function, and you've changed it only at the tau close to tau equals 0. So you see that this phase transition now becomes like a two-dimensional phase transition where, in fact, you can rotate this whole thing like we did with Kane-Fisher. You can rotate this whole thing and imagine it like a quantum two-dimensional toric code, and only in the center you have a defect where you couple the two toric code 1 and toric code 2 to each other only in the defect, and when the coupling is strong enough, you pinch off the toric code, and you condense anions at the boundary. As you know, toric code has anion condensation in the boundary, but you don't have a boundary, you only have a defect. If the defect is weak, it doesn't do anything because the toric code is gapped. So you can view it in the quantum perspective as well. So, yeah. Yeah, okay, I'm done. This is basically my summary. So this diagnosis, so you can ask, what is the physical meaning of this correlation function? One can show that it really diagnoses quantum information encoded in the anion state. So it really diagnoses whether you can protect quantum information in this mixed state or not. Yes? I'm going to be done in, so let me just finish. I have to say that also it applies generally to topologically ordered states, including non-abelian ones. It's always diagnosed via pair condensates on d-dimensional defects, so you can, using that, classify the states. There are also alternative diagnostics that we can show partially that are the same. One of them, that maybe the most intriguing one, is topological negativity that we have in this mixed state and disappears at the phase transition. And it's related to error thresholds for topological codes. Okay, so yeah, sorry for going over time.